Hello everyone, welcome to CHE 110 Excel tutorial video. Today I'm going to talk about Excel solver function. First I'm going to talk about how it's used and I'm going to talk about when you're going to use it. Now let's start by activating your solver. If you haven't used solver before, you're not going to have your solver. Normally the solver is listed under data section. It should be around here. But as you see, I also don't have it activated. So first, I go to File, I go to Options, then I click Add-ins. You see here the Solver add-in. When you select it and click Go, you can activate it by just clicking here and clicking OK. Alright, you see under Analysis section, you will have Solver. Let's see what Solver has. It has a objective cell. What's an objective cell? It's a formula cell. It will have some formulas. It will be bound by some values that are changing, which are the variable cells. The variable cells, like here, for y, the variable is x, right? Okay. And the objective is found by changing the variable cells subject to the constraint you have set before. You can add new ones, you can change the given constraint, you can delete the ones you have, etc. Also there is a constraint here. You will have this mostly defaultly selected, which means make unconstrained variables from variables non-negative. It means the x will start x will be greater than 0. Let's see. To understand how the solver works, we are going to solve an easy equation, the quadratic equation, which is y is equal to ax squared plus bx plus c. You all know this equation. Also the analytical solution. We all know this from high school. Now, my y, I have set some values here, a, b, and c. My y is going to be a times b, ay x squared plus b times x plus c. And this is going to be 2 because c is 2, even though x is 1. Now, I want solver with the root of a quadratic equation is when the y is 0. So, simply by saying, setting my objective to y, and by asking it to find the value of 0 by changing x. So when the value of y is 0, for that x, it will be the root. And I say solve. Oh, solver could not find a feasible solution. Since I click this, by making the unconstrained variables non-negative, it didn't go to the negative numbers, but the roots are -1 and -2. So by unclicking this, I make this problem solvable. So as you see, solver found the solution. All constraints and optimal conditions are satisfied, and we have found the first root, as we have found from the analytic solution. Now, since we have two roots, and since we also want to see the second root and to understand the constraints better, I'm going to add a constraint here. You can add constraints as smaller than, equal to, larger than, integer, binary, and all different for your reference cell. You can select one cell or more. It will work. Let's see. Since I want to see the root -2, I'm going to set my constraint as let the reference cell here be smaller than or equal to -1.001. Let's add this. As you see, it's listed here. You can change it, delete it, reset. Let's solve this. Okay, great. It has given -2, my other solution. But you see the y is not exactly 0, but it doesn't matter. This is almost 0, right? Because 10 to the -7 is practically 0 for this equation. Of course, the numbers you're working with are important, but for this scale, this is 0, so we can accept that it has found the 0. Anyway, this was a really simple question. So to show you, this was to show you that it's applicable for this kind of problems. How you can solve this? To show you the simple basics. Now we are going to go on to solve a question that is in your book, and we'll show you that it's also applicable to some chemical engineering problems, because that's what we are aiming for. Anyway, first of all, I have a number. This is the question 4.36. I have put the problem here, but if you can't see the problem properly, I suggest you to take your book and watch the video with it. Anyway, I numbered the streams, and let's look at the question. In the question, we have this schematic which shows an operating system. It takes beans into an extractor, and hexane into an extractor. It goes into a filter. Filter cake is removed, and it goes to an evaporator. The hexane is recycled, and the oil is taken as a product. The numbers show that 13% of the bean is oil and 87% is the solid. And also the question states that the feed ratio 1 plus 2 is equals to 3 times the beans that are fed in. These are also the filter removes all the solid, and the solid removed is the 75% of the filter cake. Let's start by doing some sheets so we can understand the question better. Total flow, hexane, solid, oil. These are in kilogram per hour. Let's copy this here. So we are going to have stream 1. I'm going to have both the numbers and names for it, so it will be simpler to check it. This will be the fresh hexane, because we feed fresh hexane into the system. Then we are going to have a stream 2, which is recycle. And we're going to have a stream 3, which is beans. Stream 4, which is filter inlet. Stream 5, filter cake. Stream 6, evaporator inlet. And stream 7, oil. Now, we don't know the inlet flow of the fresh hexane, but we know that it is 100% fresh hexane, 100% hexane. The rest is the hexane is 0% solid, and it's also 0% oil. Also, I know the recycle is also 100% of the hexane. 100% of it is hexane. Now also I can do this. So because 0% of the recycle is solid and 0% of it is oil. And I'm going to have beans. Beans, since it doesn't state how much beans are in it, I'm going to state that it's 1000 kilogram per hour, because it's the basis I take. And beans has 0% hexane. It has 87% of the 1000 and 13%. Oh, great. Also, the question clearly states that the feed ratio of the hexane, I mean 2 plus 1, is the 3 times of the beans, which means since I have decided to solve this by solver, I decided to solve it by changing the recycle total flow. So since I'm going to be changing the recycle total flow, I want to calculate the total fresh hexane with this formula. It's 3 times of the beans minus recycle. So recycle and fresh hexane incomplete 3000. 3000 plus 0, 3000. Beans 1000. Now, the filter inlet, the fourth stream, should be the summation of these. Now, let's take it like this. And it should be 4000. It will be 3000, 1000, so it will be 4000. So anyway, let's continue on. The filter cake. The filter cake will have all the solids removed. All the solids account for the 75% of all the filter cake. So it means this should be this divided by 75%. So this is all the filter cake. Now, the question states that the hexane, bean oil and hexane ratio are the same ratio in which they emerge from the extractor, which means the oil and hexane are clearly are accounted for this 25% of the filter cake, and they are in the ratio of they come in, which means again this the filter cake times amount of hexane over amount of hexane plus oil, and this is in the 25% here. Now this should, okay, as you see, this is calculated here. Alright, now it's correct. It's again filter cake amount times the oil amount over oil plus hexane amount, which is in the 25%. Okay. Now, since I know this question is made, this question is prepared to solve it simply by doing mass evaluations. So if we keep doing this, I'm going to go back to finding the recycle stream, but I don't want it because I want to use the solver add-in. So I want to do it by guessing the recycle. What I mean is, if I do this, the inlet should be this, the filter inlet minus the cake, right? It's simple. Simple as that. And I'm going to know the recycle, because the recycle should be 100% hexane, and it should be the every hexane that goes into the evaporator. So it's the answer. But let's take this number to a side to check later on if the solver calculates correctly. Now I'm going to do something like this. Since solver will be changing recycle cell, I'm going to say this number should be equal to recycle cell. Why? Because I know the recycle should have all hexane, and the all hexane that goes in the evaporator in that will go to the recycle because it's 100% recycled. So the guessed recycle will go here. Again, by simply taking the difference between this, I can find the oil amount because it's 100% oil removed. But also, I also don't want to do this. But let's make this like this. I'm going to take the difference of the total inlet and the recycle amount that is found and which is in the evaporator by the guessed by the solver. Okay, and the oil amount. The oil amount should be equal to this. Correct. Because the oil amount in the evaporator inlet will be removed. Now, We have talked about the objective function before. You have to need the objective function. Our objective function will be total mass balance will be equal to 0. What's our total mass balance? We have fresh hexane coming in. We have beans coming in. We have filtered cake and oil removed out. Of course this made 0, but it doesn't have recycle in it. So again, I'm going to go into the solver section. I want this value to be set to the 0. By changing this recycle, I want every unconstrained variable negative, non-negative, because these values cannot go negative. Or you can do this by simply, again, selecting all of this greater than 0, add this, and this constraint is same as this. Yeah, if you can't have every single variable negative, you can unclick this, set your constraints. Anyway, I also want another constraint. You can set your constraints equations such that I want this oil to be equal to the amount that is left in the system, which means I want new recycle to be selected. This recycle will go here. By taking the difference of it, it's going to find the oil amount, and it's going to check if the oil amount found is equal to the difference that the oil comes in with the beans and removed by the filter cake. So you can add your constraints, equations, inequalities, whatever. It will, if you want something to be a constraint, you can make it a constraint. The problem is set that way. The solver is set that way. Let's solve the equation. Solver found a solution. All constraints are optimal condition are satisfied. This is great. I know this answer is correct because we have checked this before. This is the number we have written by subtract of hiding the difference between this. And we all know this oil is correct because it's the simply again the difference, this inlet minus the removed. So this is correct. Also, let's check how important your constraints are to your solution. Let's say I wrote this constraint wrong. I put a minus 100 in there because that's the mistake I made. And I add this. Now, as you see, the problem will be solved because the constraint can be set. Because I've set the constraint, but this is not correct. The constraint is set in such a way that if there is a way to make it 17.9553 and it's possible to solve this, it's going to solve it. So be careful about the constraint you have set. If you might have a solution, but it may not be correct. Before stopping the video, I would like to point out, while you're working on a solver example, do not always solve on your original data. Okay, this is the data we had before. Just copy this and work on a separate sheet. Because if you make a mistake, it's sometimes easier to start from scratch and have the scratch values, I mean the starting value, is always helpful. So I suggest you have a secondary, third, fourth, whatever questions, sheets, and copy your initial values and work on them. This should make stuff easier. Thank you for listening to this lecture video. You're going to have something like this in your project. I would like to wish you good luck. Have a good day.